Okay, so if you understand how the electrons flow from the NP conjunctions, then you understand that we are actually the ones controlling it. And now all we have to do is understand how are we fulfilling the purpose of amplifying, right? All we want is to amplify the voltage, and for that, we'll look at some details. So we have the input voltage as we VE, okay, it's this one, and then we have the output one, which is VCE, which is this one, okay. So across this and this point, and the input was across this and this point, and we're calling the current which is flowing from here is IB. Okay, so if you remember, as I just showed you, from N to P, it basically breaks down into two currents. One goes into base and one goes into the collector. And obviously, the base one is so small, and the collector one is so large because of this huge value of positive potential. And so, what do we have? We found that the value of current base or base current is just the voltage across the base emitter and over its the radius inside of this junction, okay. And we say that by and we also know that the amplification factor is IC equals beta IB. This we learned in the transistor one. So all we have to do is put the value of the base current into this formula, and we have the formula of the collector current. So basically what we found here is the collector current is this many times amplified from the input voltage, okay. But this all we already know. This is the basic phenomena of any transistor. This is nothing new. The new parts are coming ahead. Then we say that um, the output voltage, we try to find out its value through some other relation, which is the VCC, which is this one. This voltage is the one we actually applied for the output one, right? And due to this one which we applied ourselves, we got the actual output, which was this one. So what we say here is we say VO equals VCE, which is the output one, and we say VCC equals ICRC plus VC. So that means that VCC is actually the sum of the output plus whatever voltage was because of this current, the current which came from the collector, which came towards the collector, or should I say, because we know that it came actually from the emitter, and it got divided into the base, and it got divided into the collector. So what the current which actually flew into the collector, the current which actually flew into the collector, it actually applies the voltage across these 2 points, this one and this one. So we have this voltage, and their sum is this voltage between them. Now, if we understand this much, we can find out that the output voltage is also given by this relation, VCC minus ICRC. And using this output voltage value, uh, we can also substitute the value of the collector current, which we found from here, which was the amplified version from the input voltage, or input current, or base current, in simple words. So we're substituting the value of the collector current, which is nothing but just the amplified version of base current. And when we substitute it, we find the final value of output voltage. And we only had to do two substitutions to get to this relation. It's nothing difficult. Now is the actual part which is new. It's different from what we have studied before. We say that we apply a tiny voltage at the input terminal B, this one, and what it does, it just increases everything by a small amount. So input voltage is increased by delta V in, and the base current is increased by the amount delta IB, and the collector current is increased by the amount delta IC. So everything is getting increased, right? But the voltage will remain the same across these 2 points, because um, we just increase the value of the current, but the ICRC wouldn't really change, right? Because this voltage isn't being disrupted. We only increase this voltage, which in turn increase these currents. So this will remain the same. And when we substitute everything, all the new values in this relation, what we found here is what we found here is that we are left with this relation where we have normal voltage, input voltage, and and tiny voltage which we have applied on top of it, and then we have VCC minus beta, and then we have the VBE voltage, which was our input voltage. It is also increased by delta V. So this was the output voltage. It is increased by delta V naught. This is the input voltage, which is increased by delta V in, and that's it. That's pretty much it. So we aren't using any currents values here. Otherwise, would have used these values as well. And now what do we do? When we do that, we subtract the values that would make up delta V naught, which is the output voltage. So simplify it. We simplify this, and what do we find? We find beta V B E, or just minus beta. We find delta V in, right? And all of this is going to be multiplied by this RCR, so we can just take it in common. So basically we solve for this, or you can just write it here for your sake, RC over RIE. Okay, so it's the same, it's the same it's the same for both. So this, I'm just trying to make a copy of it so I can show you. Okay, so what do we find here? We have this value, and we have this value, and if you notice, this one is actually the one which was here. So VCC remained the same, and we can subtract all of this. We can subtract all of this, and we are left with this and the new relation, which is this one. So this way we reach this relation, and this is such a sweet relation. It tells us something really cool. It tells us that the increase in the output voltage equals the amplification factor, which we could have found anywhere through along our way, is equal to negative of amplification factor into the small input voltage that we have increased into the RC value, which is huge, by the way, which is huge because of this voltage. We had to put a lot of resistance value for the collector, uh, so we can control the flow of current, and RIE, which is input base resistance, emitter base resistance. So this is the input resistance, which is very small. And we can see here on the next page that one sec, we can see here the gain of the amplitude is given by this relation, and the value of the factor beta RC or RIE is the order of hundreds. Why is it in the order of 100? It's because this value is so small and this value is so huge. along with the amplification factor, which is already very large, that the very small amount of voltage that we gave, the very small amount of voltage that we gave delta VIN, delta VIN, this one, resulted in very, very huge amount of delta V naught. So it's the result is substantial. Okay, the next topic we have is transistor as a switch. So as a switch, what we're trying to accomplish here is using transistors junction, NPN junction, to control on and off state of any circuit, right? So it's pretty simple. All we have to do is apply or not apply a voltage on the base. And we already know when we apply voltage here, the current starts to flow from the, it's this is wrong, obviously this is the electrons flow this way. So the electrons flow from emitter to the base and then to the collector. And if we don't apply, obviously the current won't flow. So that's all they're trying to tell you here, is that by putting the emitter collector whole circuit, this whole path to ground. See, it's in the ground, G. So when it's grounded, what it does is what it does is uh, it decreases the potential drop by substantial amounts and up to zero point 0.1 volts, and the resistance between C and E drops a lot. Like the collector and emitter have like virtually zero resistance among them. Actually, it's not zero, but it's virtually zero, or very virtually very 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 less. And what it does is it allows a large amount of current to flow across emitter to towards the collector. And if we don't apply that voltage, everything will just disappear because the resistance will increase to a very huge amount and the current will not flow. And there we they are showing all of this by using the same old relations. Nothing's new here.